So now we want to start to address issues related to fluid dynamics. Okay. So first things first, what is a fluid? So generally, um, in chemistry, there's the demarcation between solids, liquids, gases. But in physics, a good demarcation between types of substances is solids and fluids. And so a fluid is just a substance that is highly subject to shearing forces. And what this means is that the molecules, while they can be bonded, um, they don't necessarily have to be as strongly bonded as solids. So, for example, this shearing force issue is why when I put water into a container, like a pitcher, and then I can pour the water out, the water will take the shape of whatever container it's poured into, right? Whereas I can certainly take bricks and I can put them in a bucket and I can pour them out of the bucket, but unless they break or crack or something like that, they retain their shape. They don't take the shape of the container, they retain their shape regardless. Okay? So a fluid is simply a simplistic way or a colloquial way of thinking of a fluid is a material that when moved from one place to another, it just takes the shape of the container that it's in. Okay, for many purposes, that's good enough. Okay. And so the things that we want to address in this video specifically are issues related to density and pressure. Okay. So we want to kind of define these terms, right? And so, first things first, let's talk about density. And let's suppose that I have a container, maybe a vat of something, and there's some stuff in here. Think of a liquid. Why not? Okay. So, density cases can fall into two categories. Number one, your material can have a constant density. Okay. And the other option is that the density is some sort of function of spatial coordinates. So your density could be a function of XYZ if you're in Cartesian coordinates, could be a function of R theta phi if you're in spherical coordinates, whatever the case may be. Okay. For a lot of substances, and particularly, a lot of the things that you run into in your everyday lives, most liquids that you run into, um, most of the liquids that you would drink, things like water, uh, things like that, fall into this category here. Okay. If I pour water out of the tap and I pour it into a jug or a pitcher, and I take different scoops of water out of that container, I'm going to measure the same density essentially to within the error of my equipment, right? Whatever the precision of my equipment is, I'll be able to measure the same density pretty much more or less. But there's a lot of things that don't have constant density, things that have some sort of functionality to their density. Planets and stars come to mind. Okay? So a lot of celestial bodies will have a lot more mass concentrated at their centers than in their outer layers. And so the density is not constant. And this actually plays a fundamental role in both processes in both bodies, both planets and stars, um, particularly things like earthquakes and starquakes. Okay, are particularly affected by the density distribution of the material throughout the body. Okay, for most of our purposes, we're going to work with this constant density regime. Okay, and so what this means is that the definition of density, and this is the Greek letter rho, by the way. Okay, it kind of looks like a P with a curved arm, right? So the definition of density, and this is why it's going to get 3 lines. This is a definition, is mass per unit volume. Okay, that's the fundamental idea behind density, is mass per unit volume. So in SI units, this is going to be kilograms per volume, which is going to be cubic meters. Okay, kilograms per cubic meter. So those are the units. So for context, okay, 1 kilogram per cubic meter is a very non-dense substance. Okay, 1 kilogram per cubic meter would be something like even less than like styrofoam peanuts. Okay, so water, by the way, pure water is defined to have a density of 1,000 kilograms per cubic meter. And at first glance, that number might look quite high, 1,000 kilograms. But think about a cubic meter, right? So a cubic meter is a box that is a little bit over 3 feet wide, a little bit over 3 feet long, and almost 3 feet tall. It's a very big box, right? So if you have a box that's 3 feet by 3 feet by 3 feet, and I fill that with water, that's going to take several gallons, right? So we're talking like bigger than most bathtubs, right? Um, and so that's not really a cubical box, but imagine that it is, right? Where this is 3 feet, this is 3 feet, and this is 3 feet. If I tried to fill this with water, it would be a lot of water. Okay, it would take a lot of water, several gallons. So we're talking like a really, really, really large aquarium. Okay, so if you think about a really, really large aquarium and how much water is in there, then it should start to make some sense that okay, 1,000 kilograms is really not unreasonable, right? It's quite it would be quite heavy. You would definitely not be able to lift it by yourself. Um, but we use this number, 1,000 kilograms per cubic meter, to basically kind of be a benchmark for other types of substances. Okay. And by the way, this 1,000 kilograms per cubic meter it's defined uh, at 4 degrees Celsius. Okay, so the density of water is temperature dependent, and that should be obvious from transforming water from the liquid form into the solid form, ice. Ice is less dense than liquid water because it expands. So you put the same amount of mass over a larger volume, it expands, and you have that, right? Um, and but if you look at the densities for water at different temperatures, um, they don't change that much. Okay, it's usually it's less than 10% over a temperature range of about 100 degrees Celsius. Okay, a little bit over 200 Fahrenheit. So even though the density does change and it can be temperature dependent, for most of our cases, when we say, we're going to compare it to the density of water, we're going to use this standard 1,000 kilograms per cubic meter, right? But as I said, we use this kind of as a benchmark for other densities. So, for example, in the field of planetary astronomy, one of the ways that we differentiate planets is whether they are a rocky planet or a gas giant. And so rocky planets will typically have densities between 3 to 5.5 times that of water. Whereas gas giants can be about 50% of water up to about 1.5 times water. Okay, so gas giants will typically be between 0.5 and 1.5 times the density of water. So what this means is if you can measure the mass and the size of a planet, you can automatically say something about whether it is likely going to be a rocky planet. Is it solid? Does it likely have some sort of solid core? Is the core possibly iron or other heavy elements? Or is this a gaseous planet without a lot of solid surfaces? And your gases, of course, are typically going to be lower density. So your gas giants are going to have a much lower density by maybe 3 or 4 times than your rocky planets, right? And in our own solar system, just for context, Saturn is about 0.6 times the density of water. So Saturn floats, right? If you were to throw Saturn into a swimming pool, it would float, which is kind of cool. So, if your density is a function, okay, if your density is a function, then what has to happen is you have to know how that function behaves throughout your substance or throughout your material. Okay? So if I have, my mass, whatever's in my vat, and I look at a few different mass elements. So let's call this DM1, let's call this DM2, and let's call this DM3. And this is DV1, or my volume element. This is DV2. This is DV3. Okay? And so if my density is some sort of function, then I have to be able to figure out what that function is, or I have to be given the function. But what happens here is that my density isn't just, my total mass over my total volume, but my density is equal to the differential amount of mass over my volume element. And this allows me to, or this gives me a way, I should say, to calculate the mass of each individual volume element by taking dm times rho dv. And so if I know the shape, in this case, these are squares, right? So dv for squares would be dx, dy, dz. Okay? But what that leads to is some sort of integral. So my density will be a function of x, y, or z, or a combination of those. And then I can just multiply that by dx, dy, dz, and then I can integrate, and that gives me the mass of this mass element. And even though I might use the same dimensions, I might use the same size boxes for my other mass elements, they won't necessarily have the same mass if the density is not constant, which should make some sense, okay? So this principle you've seen already before with, for example, the issues of the center of mass kind of calculations and the moment of inertia calculations, right? But this idea is fundamental, okay? That for situations where your density is some sort of function, then your density is not just your total mass over your total volume. It is each individual mass element, their individual tiny amount of mass, over the infinitesimally small volume element of each piece of mass. Okay? So this is a fundamental relationship. All right, this is a fundamental relationship. So it will pay dividends to memorize and be able to work with that equation. Okay. So now we move on to the issue of pressure. And pressure, at its root level, now I'm going to try to write my pressures as P's with a bar on the bottom to differentiate from rhos. So that way we don't confuse rhos with P's. Okay, we don't want to do that. So I'm going to try to remember to write pressure with this little bar here. Okay. So the definition of pressure is that you apply a force over some area. Okay, that is the fundamental idea of pressure, is that you apply a force over an area. So for example, if you have a piston, if you can push down on that piston with some force, the piston will have some sort of area, and that will exert some pressure on the piston. Likewise, if you know how much pressure is being exerted over a given area, then you can calculate the force, because the force is going to be that pressure times the area. Okay? So, at its root level, there's really not much more to say about pressure as a definition other than we do define it to be, and let's give this one a triple thing because this is a definition. The units are, of course, newtons per square meter, and we give this the name the Pascal. Okay, we give this the name the Pascal after Blaise Pascal, the mathematician and great thinker. Okay. Now, several things need to be said at this point, and the first of which is, suppose you have a bike tire and you're going to try to air up that bike tire, and maybe here's the nozzle. Okay, there's the nozzle that you're going to put the air hose into, and so you put your pump over the nozzle, or at least connect your nozzle to the pump, whatever way you do it. Turn on your pump if it's an electric pump, or pump it by hand if it's a hand pump, and you take the hose from the pump off, and then you put a gauge on here, right? So I want to know to what pressure this tire has been inflated. Okay, so typical tires are going to be, between things like 15 pounds per square inch up to, 30, 35 pounds per square inch, typical bike tires and car tires. Okay, so like a typical car tire might be around 30 pounds per square inch for a car tire. Okay, this is typical. I am not claiming that you should inflate your tires to 30 psi. Each type of tire is going to be rated independently. You want to look at your tire specifications, but this is a typical value for a lot of different tires, particularly those with sedans. Okay. Um, Now, so pounds per square inch is a imperial unit, right? But it still is a pressure because pounds is force and square inches is an area. So pounds per square inch is still a pressure. But here's my question. Is that the pressure inside the tire? And if so, relative to what? Okay. So the whole issue is that the air inside the tire is exerting pressure outward on each rim. And actually, I'm gonna draw this bigger. Uh, let's just go ahead and do it this way. Okay. And let me see if I can do this real quick. Actually, let's leave that. Nope, nope, nope. Let's make it white. Okay. And we will put another a circle inside to actually make it like a true tire. Okay. Okay. So I have a tire, and what's going to happen is when you pump up your tire, you're exerting pressure on the boundaries everywhere. And in a closed system like this, the pressure everywhere will be the same. It has to. Otherwise, the forces wouldn't be balanced and things wouldn't work properly, right? So the forces balance by creating equal pressure everywhere. But you also have the atmosphere pushing down on the tire everywhere, pushing inward on the tire everywhere. So the air is also pushing in on the tire from our atmospheric pressure. Okay. So the pressure inside, this is what we call the gauge pressure. Okay. So this is the pressure that is relative to the atmosphere. So this just tells you how much above the atmosphere your pressure is. So really these pressure arrows should be much, much bigger. Okay. Um, but this is how much pressure you have in your tires relative to the atmosphere. So if you took your tire to a vacuum chamber, okay, so you've inflated your tire and you take it to a vacuum chamber and you remove this atmospheric pressure, right? If you remove that atmospheric pressure, then the tire would get much larger because the pressure inside wouldn't have anything pressing back on it, i.e., the atmosphere. And so the tire would just expand. And at that point, it would either expand until all of the forces inside were in equilibrium or the tire bursts, right? So those are the two choices. If you have a really, really, really strong substance, then it might be able to withstand the internal pressure, but otherwise it would burst if you took away the Earth's atmosphere or the atmospheric pressure. Okay. So there's two types of ways to measure pressure. One is the gauge pressure, and the other is true pressure. Okay. Um, what we call absolute pressure. So your absolute pressure is equal to your gauge pressure plus whatever the local pressure of the atmosphere is. Now, we define the pressure due to the atmosphere to be at sea level, right? And at about 20 degrees Celsius. So the one atmosphere is at sea level. Okay. So, one atmosphere of pressure is the pressure at sea level at 20 degrees Celsius. And um, this happens to be, well, let's put it this way. So, one atmosphere is equivalent to 1.013 times 10 to the fifth pascals. Okay, so this is honestly a lot of pressure. Okay, you don't necessarily feel this because your body is built such that yes, the pressure from the atmosphere is pushing in on you from the outside, but your internal body and the fluids inside are also pushing outward and everything is in equilibrium. So your body doesn't really notice being pushed one way or the other. It doesn't notice being pushed outward by your internal forces, and it doesn't notice being pushed inward by the gravitation or by the atmospheric pressure anyway, because everything's in equilibrium. All right. But suppose, okay, that we took all of the pressure inside something like a tire or a spherical chamber or something like that away. All right, what would happen? And this was actually done. Okay, if I remember right, it was either in the late 1600s, early 1700s, somewhere thereabout, in France, and an inventor took a metallic sphere and cut it in half and then put a nozzle on one end of the sphere or on one part of the sphere. Okay, and then he joined the two spheres together and then pumped out all the air, right? So initially there's a bunch of air molecules in here and they're just hanging out at standard air pressure, whatever the local pressure was in France that day. And then you pump those air molecules out, and even though it was a crude pump, he still got a decent vacuum seal. And so then that vacuum sealed the two spheres together. And what he did, of course, he closed off the nozzle then. And he also had he'd welded little hooks into the sphere. And he tied ropes to these. And then he put teams of horses tied to the ropes. And the horses could not pull the sphere apart. And the only thing holding it together was the atmospheric force due to the pressure, right? So you have all of this pressure, and for something like this at sea level, it's effectively coming in uniformly everywhere all around you. Okay, so there's really not a pressure differential between your feet and your head. Um, if you want to get really, really technical, there is, but it's extremely slight, right? So, the whole point here is what is the total force that the atmosphere is exerting on these two spherical shells, hemispherical shells, and why couldn't the team of horses pull them apart? Okay, so let's just do a quick calculation here. So let's suppose, I don't remember the exact dimensions, it was a decently large sphere. So let's say that the radius, was maybe, I don't know, let's just say half a meter. Okay. So force is equal to pressure times area. And our pressure we're going to take to be 1 atmosphere. And so we need to calculate the area of the sphere. Now, the surface area of a sphere is equal to 4 pi times r squared. So this is going to be 4 times pi times 0.5 meters quantity squared. And if we calculate this out, we're going to get 4 times pi times 0.25, which happens to be 3.14, which that should make sense because 0.5 squared is a quarter. A quarter cancels with 4, and we're left with 3.1415926 square meters. Now, we're not going to take all of those sig figs, right? We really, I mean, intermediate calculations, it's fine. So we can actually do that. So F is going to be equal to 1.013 times 10 to the 5th pascals. That's 1 atmospheric pressure. Times 3.14. Okay. And I get 318,243 newtons. Okay. So almost a third of a million newtons. Almost a third of a million newtons just on a sphere, a vacuumed out sphere with a radius or diameter rather of a meter. Okay, so this is not, like the largest things that's ever been built. And even just on that object, there's over 300,000 newtons of force pushing in on it. So no wonder the teams of horses couldn't pull it apart. I think there were like four horses per team or something like that. It wasn't tons and tons of horses, but still, when we think about the pulling power of horses compared to humans, it's pretty immense. And they still weren't able to do it, and it's because the atmosphere was exerting this much pressure on the sphere, right? So this whole idea of pressure is also why pressure being force per unit area. This is also why things like knives and needles work. Okay, so when you cut something with a knife, your blade has a very, very small area to it, and the sharper the blade is, the smaller the area, right? And so when you cut something with a really, really sharp knife, you can make or exert a lot of pressure on the object, even with modest to small forces, right? So when you push on something with the blade of a knife, if the blade is very, very sharp, it has a small enough area that even small forces can create large pressures, right? So even if my force is small, if my area is sufficiently small, then P can still be extremely large. And therefore you'll be able to slice things, cut things, and so forth. Hypodermic needles also apply the same principle. The tip of the needle is extremely small, and so when if you get a injection like a vaccine or a flu shot or a steroid shot or an antihistamine, whatever the case may be, the needle being extremely small, you don't need to exert a very large force to create enough pressure for the needle to then break the skin, right? And again, it just comes right back over here. Even if your force is small, if your area is sufficiently small, then you can still exert large forces, or large pressures rather. Okay, so that is just a little bit about introduction to pressure. But the next thing that we want to talk about is how does pressure change inside a substance? So suppose, going back to our vat of stuff, okay, so let's suppose I have a container and this container has water in it, okay? So I want to know what is the pressure variation with depth, okay? What is the pressure variation here with respect to depth? So here's how we analyze this, right? What you want to do is look at the free body diagrams, okay? So our water is going to have a depth of h, okay? So this harkens back to mgh, right? Now, the center of mass of the water is going to be where the weight is exerted from. So our weight is equal to mg, and it's downward, right? But remember that m is equal to density times volume, okay? Now, let's suppose this is a cylindrical container, and so the top surface of the water will have surface area A, and I have depth h. So the volume of this, or at least the water inside anyway, is going to be AH, right? So my weight is equal to AHG, right? Whoops, I need my density in there, right? Okay. But what is pressure? So remember that pressure is equal to force per unit area. So if I look at any level within the fluid, that local level is going to be equal to the force exerted down on it over its area, or the weight with which it is pressed down. So if we look at the bottom, for example, then the total weight, well, at the bottom, it is the total weight of the water that's pressing down. So the total weight of the water is rho A Hg, and I'm going to divide that by A. And so my pressure is equal to rho GH. I've just rearranged the G and the H there. So, with that in mind, what is the total pressure, let's say at this point? So, your total pressure is going to be this pressure due to your fluid, which is rho GH. But if there's pressure initially pushing down on the top of the water from the atmosphere, then you have to include that, because the higher the pressure is at the top, the more that pressure is going to be pushing down on the water totally, and that is going to increase the total amount of pressure that the bottom of the container feels. So we will often call whatever this initial pressure at the top is, we will often call this P naught, right? So we will abbreviate this equation to just say that the pressure within a fluid is equal to the initial pressure at the top plus rho GH. And this is a fundamental equation, okay? That equation is fundamental. So do keep that one in your back pocket. So the next thing is atmosphere. So what we're going to do is we're going to look at an atmospheric gas. Okay, so suppose I have, let's just suppose I look at the atmosphere, and I put or I capture a sample of the atmosphere inside a column. And within this column, man, that's a really bad cylinder. Let me try that again. And as a matter of fact, let's do it this way. Ooh. Okay. So, actually, I did that backwards. Let me undo that, and let's put, whoop. There we go. Hey, look at that. So, let's make this a very light blue so we can actually see what we're going to do with it. Okay. So I have a cylindrical column, and downward is toward the earth, upward is toward the top of the sky. Okay. So inside this cylindrical column, I just take an infinitesimally small disk. Okay. Maybe I should use solid lines, but it doesn't matter. Okay. So I have this cylindrical disc, and this cylindrical disc has width dy, okay, and it will have, it also has mass dm. Okay, it's a differential cylinder. It has differential amount of mass, differential length. And so if I think about it, there are three main forces being exerted on this piece of gas. Okay, so the first is our weight. Okay, so I have my differential amount of mass times my weight. I also have, now, here's the key point. The pressure at the bottom is higher than the pressure at the top. And if you think about it, that should make some sense just based on what we just talked about a moment ago, right? The pressure as you go down toward the bottom of a fluid increases. So my pressure down here is going to be larger than the pressure at the top. Okay? And so the whole point is that the if this piece of mass is in equilibrium, then the forces should all balance. Okay? So here at the top, we're going to call this our pressure naught. And at the bottom, we're going to call this pressure naught plus dy. Okay? And so we can now apply Newton's second law. Both the top and the bottom of the cylinder are going to have the same areas. They're going to have same area A. And so my weight is downward, as is the pressure from the top, but my pressure from the bottom is upward. So what we have here is my pressure. Let me rewrite this, because this is not P naught plus dy. This is P y naught plus delta y. Or dy. Okay. So P naught equals P at y naught. So if we call this y equals 0, then this top piece would be y naught. And this bottom piece is y naught plus dy. Okay, I should have been more formal with that. I apologize. So you have the pressure at the bottom, which is upward. And to put this into forces, we multiply this by the area. And then the pressure at the top is going to be P of y naught times A. And we also have our weight downward. Okay, so this is Newton's second law. And so what we want to do here is kind of apply some of the ideas that we've already just kind of discussed with this dm right here. Okay, so first things first, we're going to put P of y naught plus dy minus P of y naught equals dmg. But remember that dm is going to equal rho dv. And here for dv, this is just a times dy. Okay? All right. And whoops. This is all multiplied by A. I meant to put that in. So this is all multiplied by A. And the only reason we really needed to show that is because our A's cancel. All right. So now we've got P of y naught plus dy minus Py naught is equal to rho g dy. However, okay, what we're going to do is we're going to put a minus sign in here. Okay, and the minus sign is because the change in my pressure is in the opposite direction of my weight. Okay, my change in pressure is upward, but my weight is downward. So these are actually directed in the opposite directions. Okay, and I can now divide both sides by dy. And this is just a derivative. Okay. So this is saying that the change in pressure inside your gaseous cylinder here is equal to the negative of the local density times the local gravitational acceleration, right? So dp dy is going to get smaller as you go toward or away from the surface, I should say. It will get much larger going toward the surface, but in both cases, it's going to be directed opposite your weight effectively. Okay? So this is what this equation is telling you. Now, what does this have to do with the atmosphere? So, you might be familiar with the ideal gas law that says pressure times volume is equal to number of moles times the gas constant times the temperature. Okay? We can actually rewrite this for the atmosphere. It's a little bit more convenient form. Okay? So if we let m equal the mass of a molecule, and let Kb equal Boltzmann's constant, of course, rho is going to equal the density. Okay. So remember, n is the number of moles. Here. And we can write, or we can bring the density in with the idea of the volume, right? So volume is going to be equal to mass divided by density. Whoops, that should be rho. So that means that 1 over volume is going to equal density divided by my mass, right? So my pressure is equal to 1 over the volume nRT, but this is equal to rho times, or rho over m times nRT. And at this point, this is your total mass. Okay, but nRT over m as your total mass becomes the same thing as Boltzmann's constant Kb over the mass of a molecule. Okay, so putting that in, we arrive at this equation, our pressure is equal to rho times Boltzmann's constant times the temperature divided by the molecular mass. Okay? And we can now relate this to our previous result. So remember, our previous result said that the change in pressure per height was equal to negative rho g. Okay? So what I'm going to do is I'm going to put, and by the way, so this is the ideal gas law. I really guess I should have just absolutely made that 100% clear. This is the ideal gas law. And the atmosphere, our atmosphere, is a really good approximation. For an ideal gas. Okay. Our atmosphere is a really good approximation. So this is why we're using ideal gases in the first place, to talk about the atmosphere. So what I'm going to do is I'm going to solve for the density here. So my density is equal to dP dy over g. Okay? And what I'm going to do is I'm going to insert this. Oh, I need the negative sign, don't I? I'm going to insert this in for right here. Okay? So my pressure is going to equal negative dP dy kBT over mg. Now at this point, you might see where this is going. Okay? So the whole point is that I want to get an expression for how our pressure changes in our atmosphere. So I want to get some sort of function for how my pressure behaves in a atmospheric situation. Okay? So here I have pressure as a differential, and here I have my function of pressure. Okay? So I need to group my p's on the same side of the equation, and then everything else will be relative to dy. All right? So if I rearrange this equation, I'm going to get dP over P. I move everything else to the other side. It's going to be mg with a negative sign over kBT times dy. So, what kind of differential equation is this? Or not necessarily what kind of a differential equation is it, but what kind of solutions would we expect? So, this is what we call a separable equation, and we've already actually separated it out. We've got all of our p's on one side and everything else on the other. So, the solutions to dP over P are logarithmic. Where P naught is the standard pressure at the surface. Okay? Technically, this is delta y. Well, I mean, we can leave it as y if we understand that y naught is at the ground, but might as well make it a little bit more formal. Okay? So how do I solve for this? So the solutions to this are exponentials. Okay? So my pressure is going to be of some form P naught e to the negative mg over kBt y. Okay? So if you know what your pressure is at the bottom, or typically we call the ground, um, then you'd be able to calculate what the pressure is at various heights. Now, this model is assuming that your temperature is constant, and that's not a very good assumption. If you do any hiking or flying, you know that it doesn't take very long to gain altitude before the temperature can change very drastically, right? And then the other thing is that your molecular composition of your atmosphere is constant as well. And that's not always a good assumption because your atmosphere at the sea level, okay, is going to be a little bit different than the kinds of molecules you typically find at 50, 60, 70,000 feet. And they will also have different kinds of densities as well. Okay, so take this model with a slight grain of salt, but it does give you an idea for why, as you increase your altitude, your pressure drops precipitously. It's because it's an exponential decay. Okay, so this is one way to get at least an idea of how your pressure is changing. Now, I actually will say, if you can actually take the molecular distribution, the types of molecules you find at different altitudes, and adjust for the temperature, then this is a really good model, okay? But if you actually want to do non-multidimensional numerical calculating with it, you do have to make some simplifying assumptions, okay? But this is how the atmosphere behaves in general, is exponentially decaying in pressure, okay? So in the next couple of videos, we will look at Pascal's principle and Archimedes' principle and Bernoulli's principle. All right, we will see you then.